megawatts on your mind from LIGHTHIEF. We build it, we run it, we know what works, real projects, real returns. The Renewable Energy podcast that doesn't waste your time. Let's go.
We've spent considerable time discussing solar farms, how they're built, how they're maintained, what makes them tick. We've explored energy storage and biogas. We've ventured into Central Asian emerging markets. But we haven't yet properly addressed wind power, which is rather like discussing European cuisine without mentioning France. An unfortunate oversight that we're correcting today. Wind power is the established giant of renewable energy in Europe. Over 220 gigawatts of installed capacity across the continent as of 2024. Roughly 40% of Europe's renewable electricity generation. Countries like Denmark generate over half their electricity from wind. Germany has over 70 gigawatts installed. The UK has nearly 35 gigawatts, including substantial offshore capacity. Wind power isn't emerging technology or experimental deployment. It's mainstream, proven, industrial-scale generation. And investors absolutely love it. Not in the way that venture capitalists love risky moonshots, but in the way that pension funds love predictable, stable, long-term returns. Wind farms produce year after year with remarkable consistency. The technology is mature, the failure modes are well understood. The O and M requirements are established. The revenue is bankable. For institutional investors seeking stable infrastructure returns, wind power is often the preferred renewable energy investment. But wind power is also extraordinarily complex when you actually look at what's involved. A modern wind turbine is a marvel of engineering. A 100-meter tower supporting a nacelle the size of a bus containing gearbox, generator, power electronics, hydraulic systems, cooling systems, and control systems, all topped by rotor blades. Each the length of a football pitch, rotating in three-dimensional space, automatically adjusting pitch and yaw to optimize power production while managing mechanical loads that would destroy lesser machines. And maintaining these machines? That's not a job for the faint-hearted. We're talking about working at heights that would make solar panel cleaning look positively ground level. We're talking about gearboxes the size of small cars that occasionally need replacing, requiring cranes that cost tens of thousands of euros per day. We're talking about inspecting blade surfaces spanning hundreds of square meters for minute cracks that could propagate into catastrophic failures. Today we're going to demystify wind power. We'll explain how turbines actually work, not the simplified wind turns blades, blades turn generator explanation, but the real mechanical and electrical complexity. We'll discuss what O and M involves and how it differs dramatically from maintaining solar farms. We'll compare old and new turbines, onshore and offshore installations. We'll explore hybrid systems combining wind and solar. And we'll discuss why, despite permitting nightmares and local opposition and all the other challenges, wind power remains absolutely essential for Europe's energy future. At LIGHTHIEF, while our primary focus is solar and energy storage, we work with wind projects across our operating regions. We understand that the future of renewable energy isn't wind versus solar. It's wind and solar, complementing each other, filling different temporal and geographic niches, together enabling the energy transition. This episode is for anyone wanting to understand wind power beyond the superficial level, for O and M professionals considering wind expertise, for investors evaluating wind opportunities, for developers planning projects, and for anyone curious about how these extraordinary machines actually work. Shall we begin and perhaps check the wind forecast before we do? Let's start with fundamentals. How does a wind turbine actually convert moving air into electricity? The basic concept is simple enough. Wind pushes against blades, blades rotate, rotation drives generator, generator produces electricity. But the engineering reality is considerably more sophisticated. Modern utility-scale wind turbines are typically horizontal axis machines with 3 blades mounted on a horizontal rotor shaft. The entire assembly, rotor and nacelle, sits atop a tubular steel tower. Tower heights for onshore turbines range from 80 to 150 meters for modern machines. Offshore turbines are increasingly going taller, up to 180 meters or more. The rotor diameter, the circle swept by the blade tips, determines how much wind the turbine can capture. Larger rotors capture more energy. Modern onshore turbines have rotor diameters of 120 to 160 meters. Large offshore turbines now exceed 240 meters. Each blade individually is longer than a football pitch. The trend is consistently toward larger rotors, even when rated power doesn't increase proportionally because capturing more wind at lower speeds improves capacity factor. The blades themselves are engineering marvels. They're not simply flat surfaces. They're carefully shaped airfoils, similar to aircraft wings, designed to generate lift as wind passes over them. This lift creates rotational force on the rotor. The blade profile varies along its length, broader and more curved near the root where rotational speed is lower, narrower and flatter, toward the tip where speed is higher. Modern blades are typically constructed from fiberglass reinforced composite materials, occasionally with carbon fiber in high-stress areas. They're hollow to save weight, but internally reinforced with spars and webs to handle enormous bending loads. The blades connect to the hub, which mounts on the main shaft extending into the nacelle. In most turbines, the main shaft connects to a gearbox. The gearbox is necessary because the rotor turns slowly, perhaps 10 to 15 revolutions per minute for large turbines. But generators work most efficiently at higher speeds, typically 1500 RPM for conventional generators. The gearbox steps up the rotation speed by a factor of roughly 100. Gearboxes are complex, expensive, and historically problematic components. They contain multiple gear stages, typically planetary gears plus parallel shaft gears, all running in oil baths. The loads are enormous and constantly varying as wind conditions change. Gearbox failures have been a major source of downtime and cost in wind farms. This is why some manufacturers developed direct drive turbines, eliminating the gearbox entirely, using large, slow-speed generators. Both approaches work, each has trade-offs. The generator converts mechanical rotation into electrical power. Most modern turbines use asynchronous or synchronous generators, increasingly with permanent magnet technology. The generator produces three-phase AC power at variable frequency depending on rotation speed. This must be converted to grid-compatible fixed-frequency AC. Power electronics handle this conversion. Inside the nacelle, you'll find power converters, essentially very large inverters, similar conceptually to solar inverters, but designed for wind applications. These convert the variable frequency generator output to DC, then back to fixed frequency AC synchronized with the grid. This allows the turbine to operate at optimal speed regardless of wind conditions. The entire nacelle, gearbox, generator, power electronics, cooling systems, hydraulic systems, control systems weighs typically 80 to 100 tons or more for megawatt-scale turbines. It must be precisely balanced and mounted on a yaw bearing allowing the nacelle to rotate horizontally, keeping the rotor pointed into the wind. Pitch control is critical for performance and safety. Each blade can rotate around its longitudinal axis, changing its angle to the wind, the pitch angle. When wind speeds are below rated speed, blades pitch to maximize power capture. At rated speed, pitch adjusts to limit power to the generator's maximum capacity. In very high winds, blades pitch to shed load and prevent damage, eventually featherings, rotating edge onto the wind to stop the rotor entirely. Yaw control keeps the rotor pointed into the wind. Wind direction changes constantly. The nacelle must rotate to follow. Large motors drive the yaw system, which is typically a gear ring at the tower top, engaging with pinion gears. Yaw adjustments happen periodically based on wind direction measurements from anemometers and wind vanes mounted on the nacelle. Control systems coordinate everything. Modern turbines have sophisticated computers monitoring hundreds of sensors: wind speed and direction, rotor speed, blade pitch, yaw position, vibration, temperature, power output, grid conditions. The control system makes continuous decisions about pitch, yaw, and power output to optimize production while protecting equipment. This is not simple programming. The controls must balance competing objectives: maximize production, minimize mechanical loads, avoid resonances, protect against overspeed, respond to grid requirements. Safety systems are paramount. Multiple redundant brake systems exist. Aerodynamic braking using blade pitch is primary. Mechanical disc brakes on the main shaft provide backup. In extreme conditions, overspeed, grid failure, fire, the turbine must shut down safely. This involves pitching blades to feather, applying brakes, and disconnecting from the grid. The tower isn't just a passive support structure. Inside is the electrical equipment. transformers stepping up voltage from generator level to collection system level, switchgear, protection equipment. There's also a climbing system, typically a ladder with safety climb assist, allowing technicians to access the nacelle. Some towers have lifts, particularly offshore turbines, where personnel safety in rough weather is critical. From an O&M perspective, understanding this complexity is essential. A wind turbine isn't a simple mechanical device. It's an integrated mechatronic system where mechanical, electrical, hydraulic, and control systems all interact. Problems in one system affect others. Diagnosing failures requires understanding these interactions. The practical reality: modern wind turbines are reliable but not maintenance-free. Availability: the percentage of time a turbine is available to generate when wind is blowing averages 95 to 98% for well-maintained machines. But achieving this requires professional, proactive maintenance. And when things go wrong, they can go very wrong, very expensively. Let's discuss what actually maintaining a wind farm involves, because this is where wind O&M diverges dramatically from solar farm maintenance. We're not talking about walking through rows of panels with a clipboard. We're talking about climbing 100-meter towers, working inside confined nacelles with massive rotating machinery, and occasionally deploying cranes that cost more per day than some people earn in a month. Starting with routine inspections and service, wind turbines require scheduled maintenance at intervals typically measured in months. Every 3 to 6 months, depending on manufacturer specifications and operating conditions, technicians perform routine service. This involves climbing the tower anywhere from 80 to 150 meters for modern turbines, accessing the nacelle, and methodically checking systems. Climbing a wind turbine is not trivial. It's typically a vertical ladder inside the tower, sometimes with rest platforms every 20 to 30 meters. Safety systems are essential. Technicians use fall arrest equipment, harnesses, and mechanical climbing assists. In good conditions, climbing takes 15 to 30 minutes. In winter, with ice on ladder rungs or high winds making tower sway noticeable, it's considerably less pleasant. Once in the nacelle, the inspection begins. Visual inspection of all major components: gearbox, generator, power electronics, hydraulic systems, looking for oil leaks, unusual wear, loose connections, signs of overheating, checking lubricant levels in gearbox and bearings, sampling lubricants for laboratory analysis. Oil condition indicates internal wear before problems become visible. Torque checking bolts is routine but critical. The enormous forces in wind turbines cause bolts to gradually loosen over time. Blade root bolts connecting blades to hub, tower bolts connecting tower sections, foundation bolts, all require periodic checking and retorquing. Missing this simple maintenance can lead to catastrophic failures. Blade inspections are separate specialized work. External visual inspection from the ground using binoculars or drones can identify obvious damage. Detailed inspection requires either climbing the blades, using rope access techniques, basically industrial mountaineering, or deploying drones with high-resolution cameras. Inspectors look for cracks in the composite material, erosion of the leading edge from years of rain and insect impacts, lightning strike damage, and delamination where layers of composite material separate. Minor blade repairs, filling small cracks, repairing eroded edges, can sometimes be done in situ by rope access technicians. Major repairs or blade replacement requires cranes. And we're talking about serious cranes. Large turbines require cranes with lifting capacity of 1,000 tons or more. These cost 20 to 50,000 euros per day or more to operate. You don't deploy them casually. Gearbox maintenance is the most significant routine cost item. Gearboxes require oil changes, filter replacements, and bearing inspections. Oil changes on large turbines involve draining and disposing of hundreds of liters of gear oil, flushing the system, and refilling with fresh oil. This is messy, time-consuming work done in a confined space at height. But gearbox failures are the real nightmare. When a gearbox catastrophically fails, and they do with disturbing regularity on some turbine models, replacement is necessary. This involves demobilizing the crane, lifting the nacelle off the tower or opening the nacelle, extracting the failed gearbox, installing a replacement, reassembling, and commissioning. Total cost can easily reach several €100,000. Downtime is measured in weeks or months. This is why gearbox condition monitoring is critical. vibration sensors, temperature sensors, oil analysis, all looking for early indicators of problems. Catching a developing bearing failure before the gearbox catastrophically fails can allow planned maintenance during favorable weather rather than emergency repairs. Generator maintenance is similar. Routine inspection, cooling system checks, electrical testing. Failures are less common than gearboxes but still occur. Generator replacement also requires the crane and extended downtime. Power electronics, the converters, require maintenance similar to solar inverters but more complex due to higher power levels and integration with turbine systems. Cooling systems, filter cleaning, capacitor health monitoring. Failures happen but are usually less catastrophic than mechanical failures, though still expensive. Yaw and pitch systems require hydraulic and mechanical maintenance, checking hydraulic fluid levels and condition, inspecting cylinders and motors, adjusting sensors, testing response times. The pitch system is safety critical. If blades can't pitch to feather, the turbine can't shut down safely. Control system maintenance involves software updates, sensor calibration, reviewing alarm logs. Modern turbines generate extensive data. Analyzing this data to identify anomalies or developing problems is increasingly important. Some operators use machine learning systems to predict failures before they occur, allowing proactive maintenance. Offshore wind adds another layer of complexity to O&M. Accessing turbines requires boats or helicopters, both weather-dependent. Offshore technicians need additional safety training, marine survival skills, and often helicopter escape training. Working conditions are harsher. Salt spray accelerates corrosion, humidity causes electrical problems, constant motion makes working inside nacelles more challenging. Offshore maintenance logistics are elaborate. Crew transfer vessels, specialized boats designed to allow safe transfer of personnel to turbines, operate from shore bases. Personnel stay offshore for extended shifts, working on multiple turbines. Major repairs require jackup vessels, ships that can elevate themselves out of the water on legs, creating stable platforms for heavy lifting. From a cost perspective, wind O&M is more expensive than solar per megawatt. Typical figures might be 30 to 60 euros per kilowatt installed capacity, annually for onshore wind, 60 to 100 euros per kilowatt for offshore. This reflects the greater mechanical complexity, more intensive labor requirements, working at height, heavy equipment mobilization, and higher risk of expensive component failures. The skills required are also different. Wind technicians need electrical qualifications like solar technicians, but also mechanical and hydraulic expertise. Working at height certification is mandatory. Offshore technicians need additional marine and survival training. The skill set is more specialized, and finding qualified personnel is challenging in many markets. Safety is paramount in wind O&M. Working at height, confined spaces, electrical hazards, rotating machinery, hydraulic systems under high pressure, all present risks. Incident rates in wind O&M are higher than in solar. Fatalities, while rare, do occur. Professional wind O&M requires comprehensive safety programs, rigorous training, proper equipment, and a culture that prioritizes safety over production pressure. The practical challenge: wind O&M is operationally intensive and requires significant infrastructure. You need qualified technicians, specialized equipment, logistics coordination, spare parts inventory, and rapid response capability. For smaller wind farms, this overhead can be difficult to justify. This is why wind O&M is often consolidated. Single operators managing portfolios of multiple wind farms to achieve economies of scale. Let's discuss the dramatic differences between old and new wind turbines, because the technology has evolved enormously over the past 2 to 3 decades, and this evolution fundamentally affects O&M requirements and economics. Early modern wind turbines from the 1990s and early 2000s were relatively small by today's standards. Rated capacities of 600 kilowatts to 1.5 megawatts were typical. Rotor diameters of 40 to 70 meters. Tower heights of 50 to 80 meters. These machines now seem almost quaint compared to modern turbines. The technology was also less mature. Early gearboxes were notorious for failures. Control systems were simpler, unable to optimize performance as effectively. Blade designs were less sophisticated. Many early turbines used fixed-speed operation with simple induction generators directly connected to the grid, limiting their ability to operate efficiently across varying wind speeds. From an O&M perspective, these older turbines present specific challenges. The equipment is aging, approaching or exceeding 20-year operational life. Component failures are increasingly common. Finding spare parts can be difficult. Many component manufacturers no longer support 30-year-old models. Some operators resort to cannibalizing parts from other turbines or fabricating custom replacements. But these older turbines also represent opportunity. Many were built during feed-in tariff boom periods and have guaranteed revenues at relatively attractive rates. Improving their performance through professional O&M or selective component replacement, repowering, can significantly enhance returns for the remaining years of operation. Repowering is an interesting concept. Instead of decommissioning old turbines, you replace major components, new blades, new generators, upgraded control systems, sometimes new gearboxes. The foundation and tower often remain. This extends operational life by 10 to 15 years while improving performance. It's cheaper than building new, but still involves substantial investment and must be economically justified. Moving to modern turbines, those installed in the past 5 to 10 years, the changes are dramatic. Rated capacities of 3 to 6 megawatts are now standard for onshore, with offshore turbines reaching 10 to 15 megawatts and larger models under development. Rotor diameters have grown spectacularly. Modern onshore turbines commonly have rotors of 140 to 160 meters. Offshore turbines are pushing 240 meters or more. This increase in rotor size relative to generator capacity is deliberate. It allows turbines to capture more energy at lower wind speeds, dramatically improving capacity factors. This brings us to a key metric: specific power. This is rated capacity divided by rotor swept area. Early turbines had specific power of 400 to 500 watts per square meter. Modern turbines often have 200 to 250 watts per square meter, much lower specific power. This means they're optimized for lower average wind speeds, producing more consistently even when wind isn't strong. Technology has improved across all subsystems. Gearboxes are more reliable. Manufacturers learned from early failures and improved designs and materials. Direct drive turbines eliminating gearboxes entirely have proven commercially viable. Control systems are sophisticated, using advanced algorithms to optimize power production while minimizing loads. Pitch and yaw systems are faster and more precise. Blade technology has advanced significantly. Modern blades use better materials, more sophisticated aerodynamic designs, and often include vortex generators or other devices to improve performance. Blade manufacturing has become more precise, improving quality and reducing variability between blades. The evolution toward larger machines has O&M implications. More powerful turbines means fewer turbines needed for the same capacity, reducing O&M site visits and labor costs. But individual component failures are more expensive. Replacing a blade on a 15-megawatt offshore turbine is dramatically more complex and costly than replacing one on a 1-megawatt onshore machine. Height creates challenges. Accessing nacelles at 150 meters requires longer climb times and creates more safety concerns. Deploying cranes for major repairs is more expensive. The larger turbines require larger cranes with greater reach. From a reliability perspective, modern turbines generally outperform older ones. Availability of 97 to 98% is common for new machines compared to 92 to 95% for many older turbines. But when modern turbines do fail, the consequences are often more severe due to higher power ratings and greater complexity. Offshore turbines are evolving even faster than onshore. Early offshore wind used slightly modified onshore turbines on monopile foundations in shallow water. Now we have purpose-designed offshore machines with enhanced corrosion protection, improved access systems for rough weather, and advanced monitoring because accessing offshore turbines for maintenance is so expensive. Floating offshore wind is the newest frontier. Traditional offshore turbines are fixed to the seabed with foundations, monopiles, jackets, or gravity bases. This limits deployment to relatively shallow water, typically under 60 meters depth. Floating turbines mount on floating platforms moored to the seabed, allowing deployment in deep water with excellent wind resources. Floating offshore is still relatively early stage commercially. A few dozen turbines are operating worldwide, mostly in demonstration projects. But the technology is maturing, and several countries, including UK, France, and Norway, are planning large-scale floating wind farms. From an O&M perspective, floating wind presents unique challenges. Accessing turbines on floating platforms in open ocean, dealing with platform motion, ensuring mooring system integrity. The practical lesson from technology evolution: the wind industry is not static. Turbines are growing larger, more sophisticated, more reliable, but also more expensive to maintain when things go wrong. O&M providers must continually update skills and equipment to handle new generations of technology. What worked for maintaining 1 megawatt turbines doesn't necessarily translate to 15 megawatt machines. Let's discuss the fundamental differences between onshore and offshore wind, because while the basic technology is similar, the practical realities of development and operation are dramatically different. Starting with onshore wind, which is the more established and widespread deployment. Onshore wind farms are located on land. Agricultural areas, moorlands, hills, ridges, anywhere with decent wind resources and space for turbines. Europe has roughly 200 gigawatts of onshore wind installed. Onshore wind benefits from relatively straightforward access. Sites are connected by roads. Maintenance personnel can drive to turbines. Crane access, while expensive, is logistically manageable. Emergency response, if something catches fire or collapses, is possible with conventional fire and rescue services. But onshore wind faces substantial challenges in Europe currently. The easy sites are largely taken. Remaining locations often face local opposition, concerns about visual impact, noise, impact on property values, effects on birds and bats. Permitting has become increasingly difficult in many European countries. Germany, despite having strong renewable energy commitments, has seen onshore wind deployment stall due to permitting bottlenecks. France has similar issues. Only a few countries like Spain have maintained relatively favorable permitting environments for onshore wind. Grid connection for onshore wind can also be challenging. Good wind resources are often in remote areas with weak grid infrastructure. Connecting large wind farms requires grid reinforcement, which is time-consuming and expensive. In some regions, grid congestion limits how much wind can be connected. From an O&M perspective, onshore wind is relatively straightforward compared to offshore. Technicians can access sites in most weather conditions. Spare parts logistics are manageable. Crane deployment, while expensive, doesn't require maritime equipment. Response times for failures can be measured in hours or days rather than weeks. Now, offshore wind, a completely different operational environment. Offshore wind farms are located in marine areas, typically 10 to 50 kilometers from shore, in water depths from 10 to 60 meters for fixed-bottom turbines. Europe has roughly 40 gigawatts of offshore wind installed, mostly in the North Sea, with significant installations also in the Baltic and Irish Sea. Offshore wind has enormous advantages. Wind speeds offshore are higher and more consistent than onshore. There's essentially unlimited space without competing uses, no residents to complain about noise or views. Turbines can be enormous. The latest generation exceeds 15 megawatts with rotor diameters approaching 250 meters. These massive machines would be impossible to transport and install onshore, but work well offshore. But offshore wind is also dramatically more complex and expensive. Construction requires specialized vessels, jack-up installation vessels, cable-laying ships, heavy lift vessels. Foundation installation alone is major marine engineering, driving monopiles weighing hundreds or thousands of tons into the seabed, or constructing jacket foundations from massive steel lattice structures. Turbine installation offshore involves hoisting nacelles and blades, weighing hundreds of tons from a vessel to the top of a tower in open ocean conditions. This can only happen during weather windows, with acceptably low wind speeds and wave heights. Installation of a single turbine can take days and costs millions of euros. Offshore O&M is where things get particularly interesting. Accessing turbines requires either crew transfer vessels or helicopters. Crew transfer vessels are specially designed boats that can approach turbines in rough seas and transfer personnel safely. This sounds simple, but is actually quite harrowing. Imagine stepping from a boat that's rising and falling several meters onto a ladder on a fixed platform in cold weather, possibly in darkness. Weather determines everything offshore. If wind speeds exceed certain limits, typically 12 to 15 meters per second, Crew transfer becomes unsafe and must be suspended. If wave heights exceed limits, usually 1.5 to 2 meters, vessels cannot operate. During North Sea winters, weather windows can be limited, meaning turbines might be inaccessible for days or weeks. This weather dependence drives offshore O&M strategy. Technicians typically work in crews that transfer offshore and stay for extended shifts, perhaps a week or more, working on multiple turbines before returning to shore. Offshore turbines are accessed sequentially rather than individually. This requires careful planning and logistics. Major component failures offshore are extremely expensive. Deploying a jackup vessel for gearbox replacement can cost several million euros and require weeks or months to schedule. These vessels are in high demand and expensive. This is why offshore turbines are designed with enhanced reliability, and why condition monitoring is so critical offshore, catching problems before they become catastrophic failures. Offshore substations collect power from turbine arrays and step up voltage for transmission to shore via export cables. These substations are unmanned platforms requiring periodic maintenance, similar to onshore electrical substations, but with maritime access challenges. Some newer installations use remotely operated substations to minimize maintenance requirements. Cable systems connecting turbines in the array and exporting power to shore are critical but vulnerable. Underwater cables can be damaged by ship anchors, fishing gear, or subsea disturbances. Cable repairs offshore are complex and expensive, requiring specialized cable-laying vessels. From a financial perspective, offshore wind has higher capital costs than onshore, roughly 2 to 3 times higher per megawatt installed. But capacity factors are significantly better. Offshore wind in good locations achieves 45 to 55% capacity factors compared to 25 to 35% typical onshore. This means offshore generates substantially more electricity per megawatt installed, partially offsetting the higher costs. The O&M cost structure is also different. Offshore O&M costs are higher per megawatt, perhaps 60 to 100 euros per kilowatt annually compared to 30 to 60 euros for onshore. But the large turbine sizes and high capacity factors mean O&M cost per megawatt hour produced is comparable or sometimes even better than onshore. Offshore wind requires completely different capabilities from developers and operators. You need maritime expertise, specialized vessels, offshore-trained personnel, complex logistics coordination. Many onshore wind developers don't have these capabilities. This is why offshore wind is dominated by specialized players. Utilities with offshore oil and gas experience, companies that invested in building offshore-specific capabilities, and increasingly, pure-play offshore wind developers. Looking ahead, offshore wind is where most European wind growth will occur. Onshore wind will continue, but constrained by permitting and social acceptance issues. Offshore has space, excellent resources, and generally favorable policy support. The UK alone has over 15 gigawatts of offshore wind, operating with ambitions for over 50 gigawatts by 2030. Germany, Netherlands, Denmark all have major offshore expansion plans. Floating offshore wind extends the potential even further. The deep waters off coasts of Norway, Scotland, Portugal, Mediterranean regions all become accessible with floating technology. This could add hundreds of gigawatts of potential capacity beyond what fixed-bottom offshore can achieve. Right, let's discuss something increasingly common. Hybrid renewable energy systems combining wind and solar generation, often with energy storage. Why would you build these? What are the operational advantages? What are the challenges? The fundamental rationale for wind-solar hybrids is complementarity. Wind and solar have different generation profiles. Solar produces during daytime, obviously. Peak production is midday in summer. Zero production at night. Wind production is less predictable but often has different patterns. Wind speeds are often higher at night and in winter. In many locations, wind generation partially complements solar generation. By combining wind and solar at the same site, you can achieve several benefits. First, more consistent generation throughout the day and year. Solar fills daytime gaps when wind is weak. Wind provides generation at night and during winter when solar is minimal. The combined system has higher capacity factor and more stable output than either technology alone. Second, shared infrastructure reduces costs. Grid connection can serve both technologies. Electrical collection systems can be shared. Site infrastructure, access roads, control buildings, security systems, is shared. Administrative and O&M resources can be shared. The incremental cost of adding solar to a wind farm or wind to a solar farm is lower than building standalone installations. Third, improved grid integration. A hybrid system producing more consistently is easier for grid operators to accommodate than highly variable single technology generation. In some markets, grid connection is constrained by capacity limitations. A hybrid system can potentially export more total energy using the same grid connection capacity because production patterns are complementary rather than coincident. Adding storage creates further benefits. Storage can capture excess production from both wind and solar when generation exceeds grid demand or connection capacity. It can release energy during high-value periods. It can provide grid services, frequency regulation, voltage support that wind and solar alone cannot. The business case for storage often improves when serving both wind and solar rather than single technology. Practical implementation varies. Some hybrid projects co-locate wind turbines and solar arrays on the same land. This works well in locations with adequate wind resource and reasonable solar resource. The land between and around turbines can accommodate solar panels. Turbines need relatively small footprints, leaving substantial space for other uses. Other hybrid projects combine wind and solar in the same region, but not necessarily the same physical site, connecting to the same grid connection point. This provides the benefits of complementary generation and shared grid connection without requiring the sites to be perfectly co-located. Europe is seeing increasing hybrid deployment. Spain has several large hybrid projects under development. Wind farms adding solar capacity, solar farms adding wind turbines. Portugal, Italy, Greece, all seeing hybrid projects. This is partly driven by favorable grid connection policies that allow combined projects to use available capacity efficiently. Australia has been particularly aggressive with hybrid deployment, which provides useful lessons for Europe. Many Australian renewable projects are remote from major grid infrastructure with limited connection capacity. Hybrid wind-solar storage projects maximize the value of expensive connection infrastructure. From an O&M perspective, hybrid systems add complexity, but also efficiency. Operating a hybrid site requires both wind and solar expertise, but having both technologies at one location allows personnel to optimize their time. Visiting the site for wind turbine maintenance, they can also inspect solar arrays. Shared monitoring and control systems can optimize dispatch across both technologies and storage. However, hybrids also have challenges. Development complexity increases, permitting for both wind and solar, procurement of different equipment types, construction coordination. Financing can be more complex. Lenders need to understand both technologies. Some markets have regulatory structures that treat wind and solar differently, creating complications for hybrid projects. The question of optimal sizing is interesting. Do you size wind and solar equally or prioritize one? The answer depends on local resources, economics, and objectives. In locations with excellent wind but moderate solar, you might have mostly wind with solar as complementary capacity. In locations with great solar but seasonal wind, the reverse might make sense. Storage sizing for hybrids requires optimization. Too little storage and you can't effectively time-shift production or provide grid services. Too much storage and the capital cost burden undermines project economics. Typically, hybrids use relatively modest storage, perhaps 1 to 4 hours of discharge duration, enough to capture immediate production demand mismatches and provide short-term services, but not attempting full daily or seasonal storage. Looking ahead, hybrid systems will likely become increasingly common in Europe. As easy grid connection points fill up, developers will maximize value from available connections by combining technologies. As storage costs decline, wind-solar storage hybrids will become standard for new projects in many locations. Some analysts predict that by 2030, a substantial fraction of new renewable capacity in Europe will be hybrid projects rather than standalone wind or solar. The exact proportion depends on regulatory frameworks, grid policies, and site-specific economics, but the trend toward hybridization seems clear. From LIGHTHIEF's perspective, our hybrid systems align well with our multi-technology capabilities. We develop and maintain solar farms, we work with wind projects, we understand energy storage. Hybrid systems leverage all these capabilities. As the market evolves toward more complex multi-technology projects, having breadth of expertise becomes increasingly valuable. Let's discuss why, despite all the complications we've covered, institutional investors absolutely love wind power. What is it about wind that creates this investment appeal? The answer, in one word, predictability. And in the world of infrastructure investment, predictability is extraordinarily valuable. Wind farms produce very consistently over long timescales. Yes, wind speed varies hour by hour and day by day. But when you average over months or years, wind production is remarkably stable. A well-sited wind farm will produce within a few percentage points of its expected annual generation year after year for decades. This consistency comes from the physics of wind. Regional wind patterns are driven by large-scale atmospheric phenomena that don't change dramatically over time. Seasonal patterns are predictable. Interannual variability exists but is limited. The windiest year might be 10 to 15% above the calmest year, but you're not seeing doubling or halving of production. This is completely different from many other investments. Real estate rental income can vary with economic cycles and tenant turnover. Infrastructure usage can be affected by economic conditions or competing alternatives. But wind just keeps blowing year after year, producing electricity that someone needs. Compare wind to solar briefly. Solar has excellent predictability in aggregate. The sun rises every day, irradiation follows seasonal patterns, annual variation is low. But solar has zero production at night, creating daily cycling that requires either storage or complementary generation. Wind produces continuously, not constantly at full capacity, but almost always producing something. This steady baseload characteristic is valuable. The technology maturity reinforces predictability. Wind turbine technology is well established. The failure modes are understood. Reliability has improved steadily over decades. When you build a wind farm with modern turbines from reputable manufacturers, you can predict with reasonable confidence what availability and production will be over the project's lifetime. Long operational lifetimes add to the appeal. Wind turbines are designed for 20 to 25-year operational life. With proper maintenance and occasional component replacement, many turbines exceed design life. Some European turbines installed in the 1990s are still operating productively 30 years later. This long asset life allows financing over extended periods, improving returns. The revenue structures for wind projects are typically very stable. Many wind farms have long-term power purchase agreements, 15 to 20 years or longer, with credit-worthy off-takers. These PPAs provide fixed prices or clearly defined inflation-adjusted prices, eliminating electricity price risk for most of the project's life. Even merchant wind farms exposed to wholesale electricity prices benefit from wind's generation profile, producing more in winter when prices are typically higher in most European markets. The regulatory environment for wind, while not perfect, is generally stable in most European countries. Yes, there have been issues with retroactive changes in some markets. Yes, permitting can be nightmarish. But once a wind farm is built and operating with permits and PPAs in place, the probability of dramatic regulatory disruption is low. The asset is permitted, the contract is signed, and it generates predictable revenue. This combination, predictable production, mature technology, long asset life, stable revenue, is exactly what institutional investors want. Pension funds, insurance companies, infrastructure funds. These investors aren't seeking venture capital-style high-risk, high-return opportunities. They want stable, long-term, predictable returns with low risk. Wind power delivers this. The numbers reflect this appeal. Wind farms in Europe typically achieve equity returns of 7 to 12% for well-structured projects. Not spectacular by private equity standards, but excellent for infrastructure. And these returns come with remarkably low volatility. Once a wind farm is operating, the likelihood of returns dramatically underperforming or overperforming expectations is low. Debt financing for wind projects is available on very favorable terms. Banks and institutional lenders understand wind technology and economics. Projects can achieve debt-to-equity ratios of 70 to 30 or even higher. Interest rates are low, perhaps 1 to 2 percentage points over risk-free rates. This leverage amplifies equity returns while the low debt cost keeps overall project returns competitive. Portfolio diversification is another advantage. Wind generation is not perfectly correlated between sites. A wind farm in northern Germany and one in southern Spain have different wind patterns. Building a portfolio of wind farms across multiple sites and countries reduces portfolio volatility. Large wind portfolio owners achieve remarkably stable aggregate generation. The scale potential is substantial. Individual wind farms can be hundreds of megawatts. Offshore wind farms are increasingly gigawatt scale. This allows large institutional investors to deploy significant capital efficiently. A pension fund can invest hundreds of millions of euros in a single large wind project rather than assembling portfolios of many small assets. Environmental and social governance criteria favor wind. Institutional investors increasingly face pressure or requirements to invest in sustainable assets. Wind power clearly qualifies. It's genuinely low carbon, environmentally beneficial, contributing to climate goals. This ESG appeal has driven substantial institutional capital toward renewable energy generally and wind specifically. From an O&M investor perspective, wind farms are attractive because proper maintenance demonstrably protects returns. Unlike some infrastructure where maintenance is discretionary and results are ambiguous, wind turbine maintenance directly affects availability and production. Investors can see the value of professional O&M in the performance data. Now, wind isn't perfect from an investment perspective. Development risk is substantial. Securing sites, permits, and grid connection can take years and significant capital with uncertain outcomes. Construction risk exists, though using proven turbines and experienced contractors mitigates this. Technology risk is low but not zero. Choosing poor turbine models or manufacturers can create operational problems. Operational risks include lower than expected wind resource, if pre-construction wind measurements or modeling were inaccurate. Component failures, while manageable statistically, can impact individual projects. Regulatory changes, while unlikely to be catastrophic, can affect returns at the margins. But relative to other infrastructure investments, wind power's risk profile is favorable. The assets are well understood, revenue is contracted or predictable, and the fundamental resource, wind, is reliable and free. This is why wind power continues to attract capital, even when other renewable energy segments face challenges. Solar is growing faster due to lower costs and easier deployment, but wind's fundamental appeal to conservative institutional capital remains strong. Looking ahead, offshore wind particularly is seeing enormous capital inflows. The scale, predictability, and strong policy support make offshore wind attractive to the largest infrastructure investors globally. Projects requiring multi-billion euro investments are being financed successfully. Europe's path to climate neutrality absolutely requires wind power expansion. Current targets suggest Europe needs roughly 400 to 500 gigawatts of wind capacity by 2050, up from current 220 gigawatts. About half would be onshore, half offshore. This represents hundreds of billions of euros of investment opportunity over the next 25 years. Meeting these targets will require sustained investment and supportive policy. But the capital is available. Institutional investors are actively seeking wind opportunities. The main constraints are permitting for onshore wind and grid infrastructure for both onshore and offshore. If these challenges can be addressed, capital will flow. So we've explored wind power in detail, how turbines work, what O&M involves, how old and new technologies differ, the distinct worlds of onshore and offshore, the logic of hybrid systems, and why investors love wind's predictability. Key takeaways. Wind power is mature, proven, reliable technology that produces predictable long-term returns. The engineering is complex, O&M is demanding, and development can be challenging. But once operating, wind farms generate stable revenue for decades with manageable risk. Europe has 220 gigawatts of wind capacity, producing roughly 40% of renewable electricity. This will need to roughly double by 2050 to meet climate targets. Onshore wind faces permitting challenges but remains essential. Offshore wind is where most growth will occur, driven by excellent resources, available space, and strong policy support. Hybrid systems combining wind and solar, often with storage, are increasingly common. They maximize grid connection value, improve generation consistency, and allow operational efficiencies. As the renewable energy market matures, expect more complex multi-technology projects rather than simple wind-only or solar-only installations. From an O&M perspective, wind requires specialized skills, equipment, and procedures dramatically different from solar maintenance. Working at height, managing complex mechanical systems, responding to component failures with heavy equipment, all part of wind O&M reality. Professional wind O&M is essential for protecting asset value and achieving expected returns. The investment case for wind remains compelling. Institutional investors seeking stable infrastructure returns continue to favor wind for its predictability and mature risk profile. This capital availability supports continued deployment despite development challenges. Europe cannot achieve its climate goals without substantial wind power expansion. Solar is essential, storage is necessary, but wind provides the large-scale, dispatchable generation capacity that no other renewable technology can match. Offshore wind particularly will be critical. The North Sea alone could provide enough capacity to power much of northwestern Europe. The challenges are real. Permitting remains difficult in many countries. Grid infrastructure needs massive investment. Supply chain constraints occasionally limit deployment speed, but these are solvable problems given political will and appropriate investment. In future episodes, we'll continue exploring different aspects of renewable energy across technologies and markets. We'll dive deeper into specific technical topics, share more lessons from actual operations, and continue providing practical insights beyond marketing narratives. This is LIGHTHIEF, reminding you that while solar gets more attention and storage generates more excitement, wind power remains the essential workhorse of Europe's renewable energy system. The turbines keep turning, the electricity keeps flowing, and the investors keep being satisfied with predictable returns. Until next time, may your turbines face into the wind, your gearboxes stay intact, and your availability remain above 97%. And perhaps learn to love the sound of wind turbines, because Europe's energy future includes quite a lot more of them.